All right, so page 17 of your packet. Now, like I said, the connection between exponential and logarithms is that they are inverses of each other, which means that they reverse their action. So it's just like how multiplication undoes division, addition undoes subtraction. All right, a log undoes an exponential, and vice versa. And again, they're known as logarithms. So you'll hear me say logs a lot because that's how we kind of paraphrase that, but just know that the full name is logarithm. So let's actually talk about what that looks like. So on this graph and table, they graph the function f of x is equal to the x power. So it's an exponential function. All right. Now, is that function graphed one-to-one? So this is a review from unit 1. What does it mean for a function to be a one-to-one function? It passes the horizontal and vertical line test. What else? If, like, say I was just looking at the table, what has to also be true? No x's or y's repeat. All right, so one-to-one means if you're looking at a graph, it passes the horizontal line test and vertical line test. If you're looking at a table, it means no x's repeat, no y's repeat. All right. So if you look at either of those representations, whether the graph or the table, do you guys think it's one-to-one? Yes or no? Yes, it is. And it's because no x's or y's repeat, and the graph passes the vertical line test and the horizontal line test. Now, when we talked about one-to-one functions, why was it important that we knew what one-to-one functions were? What does that tell us about the inverse of a function if a function is one-to-one? So if a function is a one-to-one function, what does that say about that function's inverse? First off, when we're talking about inverse functions between a function and its inverse, what's true? The x's and the y's switch. So here's my question. If the x's and the y's switch and neither one of them repeat, what does that say about the inverse function? It's also a what? It's also a one-to-one function. I'm looking specifically for it's also a function. All right. So if it's a one-to-one function, that means the inverse is also a function. Because remember, what's the main thing that has to happen for something to be considered a function? Not one-to-one, but just a function. What has to happen, or in other words, what can't happen? Not the y values. Y values only come into play with one-to-one. It's specifically more just the x values cannot repeat. So in order for a function to be an honest to goodness function, the x values can't repeat. In order for it to be in the one-to-one subgroup, though, the x's and the y's can't repeat. So what it says about our inverse is that the inverse is also a function. Meaning the x's don't repeat. So if a function is a one-to-one function, that means its inverse will also be a function. Because remember, every function has an inverse, but not every function's inverse is a function. So every function has an inverse. Now, notice how I didn't say function at the end of that. Because not every function's inverse is a function. All right? Because sometimes, like for example, let's say I had a say I had a quadratic graph. The inverse would look like this. Is that a function? No. Automatically fails the vertical line test. That's what I mean. All right, now, since we know what the original function is, now we can graph the inverse. So what do we have to do if we want to make the table? Just switch the x's and the y's. So we're just going to switch these two rows. So my first row for the x's, for the inverse, is going to be the f of x for the top. So 1/8, 1/4, 1/2, 1, 2, 4, and 8. And then the bottom would be the other row. So this would be -2. Oops, that's -3. -3, -2, -1, 0, 1, 2, 3. All I did was flip-flop the two rows. Now, take a minute, graph those points on this same graph. So I have 1/8, -3. 1/4, -2. 1/2, -1. 1, 0. 2, 1. 4, 2, and 8, 3. So that's the inverse of 2 to the x power. Ironically, guys, this is actually, that blue graph is actually what a logarithm's graph typically looks like. All right. Because like I said, the inverse of an exponential is a logarithm. Thus, its graph will look like a logarithm. Now, let's say that I was going to solve this graph algebraically. Let's say I was going to solve what the inverse equation was algebraically. All right. What would be the first step to finding the inverse of y equals 2 to the x power? So if we're solving for the equation algebraically, what's the very first step? That's all I want, the first step. So this is a review from Unit 1. Whenever we're solving for the inverse function from its original, what's always the very first step? We have to do what? Switch x and y. So the very first step is that we got to make this x is equal to 2 to the y power. And that's all we're going to do for that step. Because once we do this, that's when we got to start knowing some stuff about logs. All right? Because as of right now, we can't solve for y just yet until we know some things about logs. All right? So, when we're defining a logarithmic function, a typical logarithmic function looks like this. Y equals log with a little subscript of a b to the x power. So we call it log of bx. And it's the inverse of y equals b to the x power. So, for example, y equals log of 2 to the x is the inverse of y to the 2x power. Now, how we get that is something that I like to call loggy froggy. All right. Now, how this works is, and you'll see what I mean in a second. So, just to note, when you have the function y equals log b of x, this b value is known as your base. Just like how an exponential has a base, a logarithm also has a base. So that little tiny number that's going to be in the subscript, that's going to be your base. All right. Now, this number right here is considered your exponent. And this number that would go right here is what we call our argument. Actually, no, I completely lied. I flip-flopped these. My bad. That's exponent. That's argument. Sorry. Now, how does loggy froggy work? Well, if I look up at the step in part D previously, the first step that I'm going to do loggy froggy is I'm just going to rewrite it so that the base of the exponent is on the left side. Now, does it matter if it's on the left or not? No, but it's more so, it just makes it easier to see what you're doing when the base is on the left side. All right. So I'm going to have 2y is equal to x. Now, whenever you do loggy froggy, you always start at the base. So loggy froggy always starts at the base. So what I'm going to do is I'm going to put a little dot right here underneath the base. Now, from the base, I'm going to go to the argument. So with an exponential, if I have b to the x is equal to y, this is the argument, base, exponent. So the next place you're going to go is the argument. So I'm going to go around and hit right here. Then I'm going to hit the equal sign. And then lastly, I'm going to hit the exponent. And we got ourselves a little froggy. Ribbit, ribbit. That's why it's called loggy froggy. It looks like a little frog. Now, what does that have to do with anything? It's basically showing the order of how you write out the function. All right. So you always start, our function will always start with log. Then we have our base. So this is where we start going through the froggy. So we have 2. That's our base. Then what goes in the parentheses will be what we hit next, which was the x. Then we hit the equal sign, so that follows. And then the last thing we had was the y. And that's it. So that's how they got the inverse function. So there was no fancy solving for y. There was no like having to move things around. We just had to do loggy froggy. So another way you can think about it is y equals log b of x is the same thing as b the y is equal to x. But this function right here would be the inverse of that one. Now, what makes logarithms so great? So what a logarithm actually does is that it gives as its output the y value. So when we do a log, the y value that we get out of it is actually the exponent that we would raise b in order to produce a certain input x value. So, for example, what's 2 to the third power? So what's 2 raised to the third power? What number? Not 8, not 6. It's 8. Now, let's do a quick loggy froggy on that. So I'm going to start at the base. What number am I going to go to next? So what's my next hit? 8. Then the equal sign. What's my last hit? 3. All right, so if I rewrite this as a log, it'll be log with a base of 2. What goes in the parentheses? What's the next thing I hit in loggy froggy? So I got the 2. What did I hit next? The 8. So that's what goes in the parentheses. Hit the equal next. And then what does it equal? 3. So if we look between the two, same expression, different form. So 2 to the third power is equal to 8. It's the same thing as log base 2 of 8 is equal to 3. So what a log does is that its input or x value is actually the number that would equal whatever we raise the base to, the power of. All right? So the base is 2, and whatever power we raise it to is going to equal 8. So 8 is going to be our input. The output is actually what you would raise the exponent to. So notice how it's a 3 here, because we raise it to the power of 3. All right? So, for example, if I did log 2 of 16, what do you think it would equal? So what's the base? 2. What's it equal? So the base is 2. What's our x value? 16. So it's basically saying 2 to the what power is 16? 4. So this would equal 4. That's essentially how you would read this log. 2 to the what power equals 16. So if I said log 3 of 27, what would it equal? 3. Because you would say this as 3 to the what power is 27? Well, 3 cubed is 27. Does that make sense how to evaluate that log? All right. So let's do some more evaluations. Now, these are some that you can do without a calculator. Now, if you can't eyeball it and tell it, you can always use Loggy Froggy in reverse and rewrite it using an exponential function. So I can always set this equal to x and do Loggy Froggy again, but this time it'll become an exponential. So just like with exponentials, I start at the base, which is the little 2. What value do you think I'll go to next? Nope. X. Then the equal sign, then the 8. So if I write it in order, I have 2 raised to the x power is equal to 8. So in other words, this is asking 2 to the what power is equal to 8. So what do you think it would be? 3. So you can either eyeball it. Guys, heads up, please. I know you guys just took an ACT, but you got to push through. You can either eyeball it and tell what it is, or if you can't really think about it mentally, rewrite it as an exponential, because it's a lot easier to see when it's an exponential. So, log base 4 of 16, what do you think that will equal to? So in other words, if I did loggy froggy, start the 4, x equals 16. So 4 to the x power equals 16. So I'm asking what power of 4 would give me 16? 2. Log base 5 of 625. What do you think that would be? It'd be what? 4. Good. So if I did loggy froggy, did it all the way around, this would be 5 to the x is equal to 625. Well, that power is 4. What about letter E? So log base 6 of 1 over 36. What do you think it would equal to? -2. Good. Because if we did loggy froggy, it'd be 6 to the x is equal to 1 over 36. Well, the only power of 6 that'll equal 1 over 36 is -2. What about G? So remember, we talked about this yesterday. I can rewrite the square root as a what? So this one I do recommend maybe converting to an exponential. So I'm going to start at the 5, swing around to the x, equals square root of 5. So 5x is equal to the square root of 5. Now, if I did the change of base method, we know we're going to keep it as a change of base of 5. So 5 to the x is equal to 5 to the something. What did I say you can change a root to? What type of exponent? So we literally talked about this yesterday. If we have a root, whether it's square root, cube root, whatever, I can always change it to a specific exponent. What kind? Do you guys remember this yesterday? You guys remember that? We literally talked about this yesterday. Come on. So, if you take a root, any type of root, so an nth root of a base raised to whatever power, you can rewrite it as b raised to that power over n. So whatever type of root it is. So here, the unspoken power with this 5 on the inside is 1. The unspoken root is a 2 because it's a square root. So what would the fraction be that I would raise 5 to be a square root? So what's my a value equal to? 1. What's my n value equal to? So 1/2. So now the bases are gone. This is the same. X equals 1/2. You guys got to know how to do this. Now this last one, I definitely recommend converting. So we go from a 3 to x to equal to the 5th root of 9. So I have 3 of the x is equal to the 5th root of 9. Now, 9, we can change it to be a base of what? 3. All right, so I'm going to rewrite this as 9 being a base of 3. So I'm going to keep the 5th root. I'm going to write 3, and 3 to the what is 9? 3 squared is 9. So if I convert that so that it looks like 3 raised to some power, so if I convert the root, so I have 3 of the x is equal to 3 raised to what power? 2 over what? 5. That goes away. X equals 2/5. So for that one, I would have recommended doing loggy froggy and then using the change of base method. Now, you can also evaluate a log in your calculator. So let me just show you how you would do that. Now, here's the thing when it comes to logarithms in your calculator. There is a log key on your calculator. However, if the log has a numerical base, meaning it has that little subscript number, you cannot use this key. Because if I click that key, it doesn't give me an opportunity to put that base in. All right, so it doesn't give me a place to put that little tiny number in there. In a minute, we'll learn that that's actually log with a base of 10. All right, that's called the common log. We'll talk about that in just a second, or we'll talk about that tomorrow. But how you would put it in so you have that little number. All right, so let's say I'm going to do, you're going to hit the math key, which is right below that green alpha key. And you're going to use the arrow keys to scroll down. Now, do you see right here where it says log base? If you click that, that will allow you to actually put in that tiny number. So I'm going to hit enter. Now I can input the little baby number. So let's just do the one we just did. So I'm going to do a little 3. Then I'm going to use the arrow key to go over to the parentheses. I'm going to go back to math because I got to put in a 5th root. You guys see right here where it says 5 to the exponent root? That allows you to put any kind of root you want in. So I'm going to put the 5th root of 9. And now it's inputted. So what I did is I hit the math key and then hit 5. So math 5. Now, when I hit enter, I get 0.4. But I want a fraction. So does anyone remember how to convert between a decimal and a fraction in the calculator? So you hit the math key again. You see how the first option says frac? That stands for fraction. So you hit enter. Enter one more time. There's your fraction. You can do that with any decimal that it comes up with, unless it's like an irrational number and you can't turn it into a fraction. So our answer is still 2/5. You can also do it in Desmos too, but you would have to go to the function key and scroll down till you see like a little log with a tiny letter and another X. All right, so that's evaluating logs. Now, so something you need to remember about logarithms is that they give exponents as their outputs. So their y values are actually the exponents. All right. Okay, guys, come on, heads up, or you'll be standing up. Now, if the function is this, which of the following would represent its y-intercept? So when it comes to a logarithm, you could graph that in Desmos and get it. All right. But its y-intercept would be whatever value of x, if you put it in here, would give you 0 for y. So the y-intercept is actually this number right here. So whatever number is being added or subtracted outside of the parentheses of the logarithm, that's the y-intercept. So the y-intercept is actually 9. Now, for number 4, it asks what two consecutive integers must log 3 of 40 lie? So in your calculator, go ahead and put in log 3 of 40 and see what you get. So remember, hit the math key, scroll down until you see log base, and then you can type in your expression. So if you don't have a calculator, I recommend you grab one. So you need to know how to do this. So again, just for help, how to put a logarithm in again. You're going to hit that math key, which is underneath the alpha, that green alpha key. You should get this screen. You use your arrow keys and scroll down until you see log base. So you should see log and then base in capital letters. You can hit enter then once your cursor's highlighting it. Now I know it's hard to see because of where the projector is, but if you can see it, it's currently blinking over where I would put the little number. So I'll put the 3 there. I'm going to use my arrow key to shift to the parentheses spot. I'm going to type in 40. Does everyone understand how to put it in your calculator? If I hit enter. So that's what I get. Now it's not going to be a pretty fraction because that's definitely an irrational number. Logarithms can create irrational numbers. But what two whole numbers is that number in between? 3 and 4. So our answer for this problem would be number 3. Now, last thing we're going to talk about, and then we're going to take a break. So I'm warning you now, today's going to be pretty note heavy. Okay? Now, there's something else we need to know about logarithms. So there's 2 special types of logarithms in mathematics. All right? It's kind of like the standard one. It's the whenever when you get deeper into math, you start seeing less and less of logs with tiny numbers as their bases, and you start seeing more of. We start using the more applicable uses of them. You start seeing these more special types of logs. So the first type of log that is really special is log base 10 of x. And we call that the common log. So remember how I said not to hit that log key on your calculator if you're trying to evaluate a base with a tiny number in it? That's because that log key is actually the common log key. Meaning, if you plug that in, log of x is the exact same thing as log base 10 of x. So in my calculator, if I click just that log key right next to the 7, that inputs automatically the common log. So the log that's popped up here is log base 10. All right. So if I do that first problem and I type in 100, what do you think I'm going to get? 2. So that's why I said don't hit that log key if you have a base like a little tiny number in the subscript, because that log key just inputs log base 10. So this would be 2. What do you think 1 over 1,000 would be? -3. What do you think the square root of 10 would be? 1/2. Now, the other type of log, and it's not on here, but I just want you guys to be aware of it. The other type of log is called the natural log. And what the natural log is that it is log with a base of e. So you guys remember the other day when we talked about the special number e that we use with like exponential functions like PERT? Log base e is called the natural log, which you'll see it a lot as ln of x. All right. Now, you'll probably see this one more in Math 4, but just be aware that that's the other type of special log. So the two special logs are common log, which is log base 10, and natural log, which is log base e. So on your calculator, if you look right here, this ln key, that's log base e. Now, both of these logs have a very special use. We will use them more when we're solving exponential equations without like bases. All right, so we'll talk more about that tomorrow. But for right now, I just want you to be aware of their existence. Okay, so here's what we're going to do. We're not done with notes yet, but just to wake you guys up a little bit, we're going to take a 4-minute break. You can use the restroom if you want. You can just sit and chill, whatever. When we come back, we're going to do page 21. So when we come back, we're going to pick up at page 21. All right. So make sure you're back in this room by the time that timer goes off. All right, let's come back together. All right, so page 21 of your packet. Now that we talked about what logs are, we're going to look more specifically at some key features of their graphs. All right. So before we talk about log graphs, we talked about exponential graphs on the very first day of this unit. All right. What is true about an exponential graph? So does anyone remember what the domain is usually like for an exponential graph? A domain for an exponential is always going to be what? Let's review, guys. Domain for an exponential is always going to be what? Open up your journal and look back at it. It's in your journal. So take out your journal and look back at it because I'm not telling you. So it's in that foldable that we did. What is always the domain of an exponential function? Right, negative infinity to infinity or all real numbers. What's always the range? Nope. So it's a number typically to infinity. What is that number? Where does it come from? It comes from the exponentials what? So do you guys remember that line that it can't cross? What's it called? The horizontal asymptote. So that number comes from the line that it can't cross, which is the horizontal asymptote. It's just a horizontal line that your graph doesn't cross. All right, so the one that we graphed in the journal, that was y equals 0. So that's why the range was from 0 to infinity. So let's look some more at these graphs. So now we're going to graph the functions log 3 of x and y equals 3 of the x. So remember, they're inverses of each other. So if we do 3 of the x power first, what's 3 of the negative 2 power? 1 over 9. What's 3 of the negative 1 power? 1/3. 3 of the 0. 3 of the first. 3. 3 of the second. Nope. 9. Now, we're going to take a minute, graph that function. So I have negative 2, 1/9, negative 1, 1/3, 0, 1, 1, 3, 2, 3, 6, 9. So the exponential looks like this. What do you guys think my horizontal asymptote is? What line does it look like that graph is not going to cross? 0. So my horizontal asymptote is the line y equals 0. So right here. Because if you think about it, what will happen is that as we get into further down the negatives of x values, we'll just keep getting smaller and smaller and smaller fractions, but we'll never actually get to 0. There's no power of 3, so you can't raise 3 to any power and get 0. That's why. Now, since these two functions are inverses of each other, the table for log base 3 of x is really easy because what do I have to do? If they're inverses of each other, you just gotta flip the x and y's. So the x values now are 1/9, 1/3, 1, 3, and 9. And the y values are now -2, -1, 0, 1, 2. That's a nice thing about inverses. Once you got one, you can find the other just by flipping the table. So if I graph that, I have 1/9, -2, 1/3, -1, 1, 0, 3, 1, and then 9, 2. So here's my logarithm graph. Now, here's my question. We know that an exponential has a horizontal asymptote. But if we look at the logarithm graph, it crosses that asymptote. So it's not going to be the same, even though they're inverses of each other. But a logarithm does have an asymptote. So think about this carefully. If they are inverses of each other, and an exponential has a horizontal asymptote, what type of asymptote do you think a logarithm has? A vertical. What do you think it is? Well, think about it. If we switch x and y for everything, what do you think it is? X equals 0. So our vertical asymptote for our logarithm is x equals 0. Because if y equals 0 is our horizontal asymptote for the exponential, and they're inverses of each other, that means x and y flip. So this y becomes the x for its inverse. So my vertical asymptote, instead of being the x-axis, is the y-axis. So same thing, but it will get incredibly close to the y-axis, but it'll never actually cross it. So you'll never have an x value that will equal 0 and be defined as that block. And the reason for it is, for example, in your calculator, just hit the log key and put 0 in and see if it gives you anything. So what does it say? Error. What type of error message is it? Domain. All right. That's because log of 0 is always going to be undefined. That's why it says it's a domain issue, because it's affecting the domain of the function, which we're just about to talk about. So this orange graph is y equals 3 to the x power. The green function is y equals log 3 of x. Now, if we look at the orange graph, what's the domain? So if I'm looking at this exponential graph, what's the domain? What did we say earlier? That an exponential graph is always going to have the domain of what? All real numbers. So you can either say it's from negative infinity to positive infinity, which just means all real numbers. What about the range? What's the lowest possible y value of that orange graph? 0. But would I use a bracket or a parenthesis? We use a parenthesis. Why? What's true about y equals 0 for the orange graph? It's where the what is. It's where the horizontal asymptote is, meaning our graph will never cross it. You'll just get infinitesimally close to it. So technically it's undefined at 0. So that's why we use a parenthesis, not a bracket. Bracket means defined, parenthesis means undefined. So our range goes from 0 to infinity. And remember, you can also write that as y is greater than 0. Now, what about the green graph? What's the domain of the green graph? Say it again. Nope. 0 to infinity. Because our leftmost x value, we're going from left to right. Our graph doesn't even start until x equals 0. Now, when I write from 0 to infinity, will I use a bracket or a parenthesis for the 0? Parenthesis, because that's where the horizontal asymptote, not the horizontal, the vertical asymptote is. This would be from 0 to infinity, which we can write as x is greater than 0. What about the range? What do you think the range is going to be? What's our lowest possible y value? Nope. And negative infinity. Let's see this arrow right here? It's going to go down forever. What's our highest y value? It's also going to be infinity. Because even though it's going up very slowly, it's still going up. All right, because of that arrow. So it looks like it's leveling off, but it's actually not. That graph will make it to 1 million eventually. It'll probably take 20 billion years, but it will make it there eventually. So it keeps on going on forever. So your range is from negative infinity to positive infinity, which we can also say is all real numbers. What do you know about the domains and ranges of those two functions? They flipped. Why do you think they flipped? Because they're inverses. So, if you look between the two domains and the ranges, they flipped. So, an exponential's domain is always all real numbers, whereas the range is always the horizontal asymptote to infinity. On the flip side, the domain for logarithm is always its vertical asymptote to infinity, but its range is all real numbers. So that's how you can remember. They literally just flop. If you remember it one way, the other way is easy. So without even calculating or even drawing this next graph, what do you think the domain of log base 10 of x will be? What do you think the domain will be? 0 to infinity. So what we'll learn in a little bit is that the horizontal and vertical asymptotes are controlled by whatever's being added or subtracted to the x within the parentheses. All right. But in this case, there's nothing there, so nothing's happening to it. What about the range? What do you think the range is? Negative infinity to positive infinity, or you can say all real numbers. So guys, if this was a question on your test, my recommendation, just graph that function in Desmos. Usually the horizontal and vertical asymptote is really obvious because you'll see like where the graph levels off. You just got to know that a logarithm has a vertical asymptote, or exponential has a horizontal asymptote. All right. And one of them, whether it's your domain or range, is going to be all real numbers. The other one's going to be from whatever your asymptote is to infinity. So let's look at this one. So example 3. Now, here's my question. This is a logarithmic graph. Where does it look like the vertical asymptote is? So what line does it look like my logarithm graph is leveling off at? It looks like it's about right here. All right, so right here would be about where my vertical asymptote is, which is x equals -3. Now, if this was a question on your test, all I would do for this is graph all 4 of those functions in Desmos, find a couple of points that match up, just make sure they have the same vertical asymptote. All right, but I do want to show you how you can figure out where the vertical asymptote is. So, based off of the vertical asymptote, just from looking at the functions, I will say right now the vertical asymptote is typically in the function in some shape or form. I will tell you right now, you can go ahead and eliminate the first answer choice. The way we get the vertical asymptote is whatever is in the parentheses of the log. So typically for a log function, you have log base b of x minus h plus k. That's typically what a log function looks like, and you got an a value in front. Your vertical asymptote comes from the x minus h. So this is where your vertical asymptote is going to come from. And how you get it is you're going to set whatever's in that parentheses equal to 0 and solve for x. So for example, in this case, if I solved it, x would equal h. So based off of that knowledge, which other of these 3 functions can I eliminate? I can eliminate 2, because if I set x minus 3 equal to 0, I will not get -3 as my answer. I get +3. Because x plus 3, set it equal to 0, subtract the 3 to both sides, x is equal to -3, which is my vertical asymptote. Now, from there, it's just kind of figuring it out. So again, what I would do here is put in Desmos and then match up a couple of the points. So let me see. So this one would be this. So again, if this was on a test, just plug all these answer choices into Desmos, get a couple points off of it, match up. Now, it also helps us determine the domain. So, for example 4, finding the vertical asymptote helps us find the domain. So, if we want to find the domain of this function right here, what do you think I'm going to do first? So, the first thing I'm going to do is find the vertical asymptote. What did I just say you do to find it? Take whatever's in the parentheses, set it equal to 0. So this would be 3x minus 4 is equal to 0. I'm going to solve for x. So if I add 4 to both sides, I get 3x is equal to 4. Divide by 3, x is equal to 4/3. So this number right here, so this number right here, that's my vertical asymptote. So if that's my vertical asymptote, and what we know about the domain of logarithm functions, what do you think how we would write the domain out is? What do you think my lowest x value would be if that's the vertical asymptote? So recall the previous page. All right. Our domain always started with our what? It started with whatever the vertical asymptote was. So what's my lowest number here? 4/3. So it's going to start at 4/3. And it's going to go to where? Infinity. So again, the domain of a logarithm is always whatever the vertical asymptote is, and it's going to go to infinity. Now, that's not necessarily always true. The only time it's not, like it flip-flops, is if that logarithm, if there's a negative in front of this logarithm, but we won't really deal with those in this class. All right. All right. So the last thing that we're going to do, take out your journal. We need to finish up that last little piece of the 2.1 foldable, which is the logarithm side. So be quick because we're just restating what we just already stated. So take out your journal. We're going to go to the 2.1 foldable. We're going to finish up the logarithm side. I told you guys, it's a note-heavy day. Tomorrow will not be as bad. All right, so logarithmic functions. Don't forget, b is your base, x is your argument, and f of x is technically your exponent. All right. Now, some things to remember. The only type of logarithmic graph that we're dealing with is a strictly an increasing one. So this one is strictly increasing. And that's the only way we're going to be dealing with logarithms. They're going to be strictly increasing in this class. And just remember, they always have a vertical asymptote. So it would always be x is equal to some number. That's how you would write it. So if I go on the inside, I can tell you right now that this logarithm that they want us to graph, y equals log 2 of x, is the inverse of 2 to the x power, which we have graphed over on the other side. So what would I have to do for the table? It's very easy. What do I need to do for the table? Just flip the x and the y values. So this would be 1/8, 1/4, 1/2, 1, 2, 4, 8, and just to finish it off, the next one would be 16. Even though it's not there, just trust me. Or not the x values, the y values would now be -3, -2, -1, 0, 1, 2, 3, and 4. So when we graph it, it would look like this. So 1/8, -3, 4th, -2, 1/2, 1, 2, 1, 4, 2, 8, 3, and then we're not going to graph that last point because it'll go off the graph. So our graph will look something like this. So this is the graph y equals log base 2 of x. What would be the vertical asymptote here? So if I set what's in the parentheses equal to 0 of the log function, what's the asymptote? X equals what? 0. So my asymptote would be right here at x equals 0. So I have a vertical asymptote, I will in a second, at x equals 0. So what's the domain? Nope. 0 to infinity. It's the vertical asymptote to infinity. What's the range? What's the range? Negative infinity to positive infinity. So remember, we can rewrite this as x is greater than 0 and all real numbers. So just remember, this is all, the range is always the same for any logarithm. So the range is always the same for every logarithm. It's always going to be all real numbers. The domain is based off of the vertical asymptote. So if you have x equals some number, your domain will be some number to infinity. Any questions on logarithms? All right. So your assignment for today, you have 2 different quizzes, not delta math, quizzes. All right. So you have 2 different quizzes. They're already assigned to you. If you are not a part of my quizzes class, you better go to that announcement that says join the class for quizzes and get on there because there's like 4 of you that are not in there. If you need help, talk to me. So you guys got a solid 15 minutes. So get at least one of them started.